Okay, so in this problem, we are going to use conservation of energy. I actually really like this problem because I think it's not tricky mathematically, but there's some conceptual things going on here that I think are very important. There was one problem, I encourage you to refer back to it before looking at this one, where there was like a marble in a bowl that was rolling, and the first half had friction, and the second half did not have friction, basically. Um, so please look at that one before, because I think that it introduces the concepts that you're going to need to look at this problem. Sorry, I just tapped the mic. Okay, so in this problem, we have a figure. Okay, there's a disk with this mass m, okay, and there's an axle through the center of the disk. So this disk is on a table and it's connected to the axle with this spring, and the spring has a spring constant k. So this is the equilibrium position, right? So when a spring is at equilibrium, there's no energy. So there's no potential energy from stretching it where it wants to like get back to that original equilibrium position. And there's no potential energy from compressing it where it wants to get back to that initial equilibrium position. So it's at rest when it's at equilibrium, okay? So the surface to the left of the spring is frictionless, while the surface to the right of this actually does have friction, okay? So the sphere is stretched. So this is where we start, just at rest. And then the sphere is stretched to distance a, right, to the right, and placed on the table. And then it's let go from rest. So if the sphere rolls without sliding, so keyword here, rolls without sliding, when friction is present, what is the maximum distance b that the spring will compress, okay? So if we stretch it a and then we let it go, we're trying to figure out some maximum distance b at the end where that spring is going to end up being some kind of compression here, right? And so that compression is going to depend on the kinetic energy, right? It's going to depend on how much we're moving it, right? How much kinetic energy is going to go back and just basically smoosh that spring. Okay, so really important thing here that I think is very interesting is, so because we have friction, right, that's actually what gets this disk started from this point here to here. We're causing this rotation due to the friction on the surface, right? It's rolling without slipping because of that friction, and so that's getting that disk started. So that means that we are going to have some rotational kinetic energy by the time we get to that middle point. So if I call this like, I forgot how I labeled these points before when I was looking at it, but I'm going to call this like, we'll say like 1, because we have the potential energy, 2, and then 3. Okay, so when we do conservation of energy, we find the change in energy between points in a system. So we're going to look at, first of all, we're going to go from point 1 to point 2. Okay, so we're going to look at the initial energy in point 1, and then we want to see, so this is, we're going to call this the first one, and then we're going to see how it changes when we get to point 2. Okay, so we are going to use, so K E plus PE plus work, KE plus PE. Okay, if the object is rolling without sliding, we don't actually have work due to friction. That energy is just being converted into rotational kinetic energy. So we actually don't have a work term here, which I know is a little bit weird when we're dealing with friction. We're used to having this like work term, but we don't have any sliding. If there was some sliding, right, like if it wasn't, so this, with this static friction, or if we have rolling without sliding, it's like the static friction is acting on the object. But if there was some sliding, then we would have, you know, some of this work term where energy would be taken away in the form of work. Okay. All right. So let's look at 1 and 2 for each side. Okay. So for this side, for where the spring is here, we just have the potential energy of the spring, right? The spring has been stretched. We have the spring potential dependent on this distance A, right? So that's what's going to be on our other side. So we don't have any kinetic energy at the beginning at state 1. So Ke is equal to 0. And then the potential energy is just the spring potential, right? 1/2 Ka squared. A being that distance x for the spring displacement, okay? So we can just plug it in. All right, so then we have 0, right, for our work. And then what about our potential energy at point 2? Do we have any potential energy there? No, because point 2 is actually our equilibrium position. So once we get to that equilibrium position, all of our spring potential energy will be gone. But this guy will be moving, right? We're going to have an object that has rotational. It's rotating because we have that roll without slip. It's going to be rotating and it's going to be moving. So we're going to have rotational velocity, right? And we're going to have a linear velocity. So we're going to have two kinetic energies, okay? So we're going to have the rotational kinetic energy of 1/2 IW squared, W squared, and then we're going to have the 1/2 mv squared. Why do I do this? Mv squared. Okay, so we have both, right? So what was the term for m? Was it capital M? Yeah, sorry, they give you capital M for the disk. So let me stick with their sign convention. I have a habit of changing those and then confusing myself, so I apologize. Okay, cool. So what is I for our disk? Can we simplify this at all? Well, we know that I for a disk equals 1/2 mr squared, right? Just for general disk. So this general expression from our lookup table. So let's maybe simplify things a little bit because we're asked to figure out here. Oh, we want to know the maximum distance that it'll compress. So we're trying to solve one step ahead, but we're just going to simplify things a little bit, and then it's going to kind of make sense why we're doing this. So I'm going to do it without telling you, or not without really explicitly showing you, and then you're going to kind of see at the end. Okay, so our velocity is equal to linear velocity is equal to the angular velocity times r, right? Because we know that we have a roll without slip condition. So when we are rolling without slip, we can do two different things, right? So this is important because this problem is modeled in two parts, right? At point 2, right instantly at point 2, this roll without slip condition applies, and we're using the potential energy from the spring was all converted into rotational and kinetic energy in this roll without slip condition from 1 to 2. But from 2 to 3, roll without slip doesn't apply, okay? So we're modeling energy between 2 points. We can do roll without slip from 1 to 2, but from 2 to 3, we can't, okay? So what we want to do is we want to find that initial linear velocity here because we need that initial linear velocity here to tell us how much of that spring is going to be compressed to B, okay? So we're going to solve for our linear velocity B. Okay, so we're going to substitute some things in our equation. So we have 1/2 I, and then we're going to sub out our W for V over R, right, squared, plus 1/2 MV squared equals 1/2 KA squared. Okay, so with some fun algebra, I'll give you our final answer and then I will algebraically kind of work through it. So feel free to skip ahead if you want to not watch me solving algebra, that is totally fine. But I'll give you the final answer for this and then we'll work through it. So V, when you solve for everything, is going to be equal to 2K over 3M, right, times A, okay? So here's where I go into some algebra, so feel free to skip ahead to the next part where I do the kinetic energy, or do the conservation of energy from 2 to 3, okay? All right, so the ugly algebra here, let's get that in the right form. Okay, so we can cancel out our halves here, 1/2, 1/2, 1/2. We have, let's see, mv squared and r. Oh, and then let's put in our I here. So I is equal to, what was our I term? 1/2 mr squared, right? 1/2 mr squared for our I term. And then we have v squared over r squared plus mv squared is equal to ka squared. And we're trying to solve for v. Okay, so we can cancel out this other r squared. Let's see. Then we have, if we group these guys, we're going to end up with, so we have 1/2 m, right? V squared plus mv squared equals ka squared. Let's group the m's. So 3/2 m v squared, is that starting to look right? Yeah, okay, is equal to ka squared. So then we have v squared is equal to ka squared and then we have 2/3 m. So 2m over 3 is going to, or sorry, 3m over 2. I'll rewrite this way, 3m over 2. Just be careful when you're dividing your fractions because I see a lot of errors like this. Ka squared and then times 3, sorry, I'm flipping this because I'm dividing the other side, right? 2 over 3m. So I want to divide the other side by 2 over 3m. Okay, then I'm going to take the square root of both sides, and I can pull that a term to the outside because it's squared. So I have v is equal to 2k over 3m square root times this a. And that should be, yep, that is correct. Okay, cool. So I did the algebra and I found that v. Boom, all good. Okay, let me scooch this guy over so you can tell that. So this is just my algebra. Divide that. Okay, so step by step there. All right, so that was from 1 to 2, right? We found that from 1 to 2. All right, so now we have the velocity. Now we want to go from 2 to 3 because we're trying to find this b displacement, okay? All right, so what do we have going on from 2 to 3? So let's do this way. So we have 2.2, and then we're going to set it equal to 0.3 for a conservation of energy. So 0.2, what did we have for 0.2? Well, we had this mess over here. We had 1/2 IW squared, right? Plus 1/2 MV squared. So I'm just taking that original expression. Okay, just to avoid confusion by simplifying anything yet. And then because this surface is frictionless here, that disk is basically going to be like spinning out. The rotational kinetic energy is not going to be converted back into linear kinetic energy. Same thing like we saw with that half pipe with the marble. So it's kind of going to be, it's going to be spinning out. So we're not going to have as much linear velocity because we're losing some of that energy to that spin out. So the final expression, so what's going to be happening by the time we get to point B is this disk is going to be still spinning, right? But we will still have some potential energy for the spring, right? So we're going to have the potential energy for the spring because it's going to be smushed a little bit. But then this disk is also going to be rotating, okay? So this is kind of a conceptual problem. So what's happening at the end? We have this 1/2 K, and then B is the distance, the compression of the spring, right? 1/2 KB squared. And so that's the maximum, right? Plus 1/2 IWF squared. Okay, so how do we find this? Oh, sorry, WF. This is going to be the same W, right? Because it's not going to take away from the angular velocity after we leave that frictionless area. So this IW squared is going to be equal on both sides. That's why I left it and went kind of back to the initial. I'm like just sort of foreshadowing here. Okay. All right, so we need to solve for our B term here. Okay, so, and just to kind of recap what's going on, it's rotating and moving linearly by the time we get to here, but we lost all the spring potential energy because we got back to the equilibrium point, and now we're going to add some more spring potential energy by squishing it in this direction, but because this surface is frictionless, it's going to continue to rotate. So this one is more of a conceptual problem here. Okay, so we can cancel out these terms, right? Because they're the same because that angular velocity isn't going to change because we're just totally sliding here, right? This is a full slip condition, frictionless. Okay, we have no, so this is frictionless surface, full slip condition. And there's no like applied force to like roll along it or anything. Okay, so then we have 1/2 mv squared is equal to 1/2 kb squared. So then mv squared is equal to kb squared. So let's say m over k v squared is equal to, sorry, b squared. So b is equal to the square root. I'm just moving this around, sorry. M over k. And then just multiply by v, I think, on the outside here. M over k, right? V. Let's see if this works out. If I need to double check my algebra skills here. Okay, so we've got this. Copy, paste. So this is our v here. So we're plugging in this v. let's talk about kind of how we would simplify things in the square root. Square root of m over k, right? And then we're multiplying by another square root. I'm going to pull out the terms that we do have, right? So I'm just putting that v in there. Square root of 2k over 3m times a. Okay, so we can combine the square root, right? M over k, 2k over 3m, right? Square root times a. Okay, and then we can cancel. So we can cancel this k, we can cancel this m, right? By pulling it in. So we're going to end up with square root of 6/3. What happened here? What did I drop? So I have square root of 2/3 a, and I should have 6/3. Square root of 2/3 a. And it should be equal to square root of 6/3. So let's see what happened here. Did I forget something? 1/2 kb mv over k. So the solution that they have for this problem is square root of 6 over 3a. And I can't help think that I might be missing something. So I'll leave it up to you guys to kind of backtrack on me here and see. So the first one is correct. It's 2k over 3ma. And they all have a 1/2 term. Yeah, I guess I just don't see where that happened there. I'll leave it up to you guys to point this out. There might be a small mistake in the solution. I will go back and kind of double check this. But just notice that there is a discrepancy here. So just by a factor of 2 in that denominator. So it might have been, yeah, I don't know. I don't know what happened there. Interesting. Yeah, if you want to leave in the comment section below if you think you can tell where I went wrong. Otherwise, there might be a mistake in the solution. I couldn't tell you. I will backtrack on this and kind of like leave a comment later to kind of as a clarifying point. But the notes for this one should be in the description if I do make a correction. Okay, moving on to the next problem. But just sort of as a high level overview for all the steps that you are applying here, from 1 to 2, you have the kinetic energy converted to, or potential energy converted completely to kinetic energy, and then all of that kinetic energy going back to spring potential energy, but we do still have this 1/2 I W squared term, right? Because we go from a surface with friction to a frictionless surface where it's spinning out.